I'll get started, and if we decide we need it or it turns on, it turns on. But it's kind of strange to be here because I think most of the people out there know more about this stuff than I do. But nonetheless, Paul Amber talked about doing this, so here I am. And so we're talking about the tritium technology of Mound. That kind of came along after a lot of the neat stuff was already in place. Program and G building was well underway. And so we can go to the next slide. Basically, we're going to talk about what is tritium, what did Mound, how did Mound safely handle the tritium, how did we measure it, and how did we advance tritium technology. I think we're going to find, and we all know that tritium technology, Mound did a whole lot to move that forward. When I talk to people that come through our shop about tritium, I try to relate to something they're used to, and that is the Spider-Man movie, where tritium was actually on the big screen. This villain, Doc Ock, had tritium, and he was making fusion and doing all kinds of evil things with it. But it was interesting that they actually introduced tritium that way. As all of you probably know, tritium is just an isotope of hydrogen. So just think of hydrogen, and that's what tritium is going to do. Difference being a couple extra neutrons and some unstable behavior. So tritium is kind of tough to detect. It's kind of weak compared to other isotopes, and so it's hard to see. It's hard to capture. Tritium gets out, it moves quickly. Okay. Where's tritium used? Well, the exit signs we had all over Mound. Pat right now is looking for somebody to clean up a bunch of their exit signs. So if you know anybody that wants to recover some tritium and can, there's some money for it. Watches, gun sights, binocular sights, anywhere where you had wanted to have self-powered light. Neutron generators. We see a lot of people today interested in oil drilling, going deeper and deeper, and the neutron generators are another area for tritium. What we're all used to is the use of tritium in the weapons. When we advance the weapons to the thermonuclear type, that's a big mission here at Mound. That was the use of the tritium in the weapons. Strangely enough, today when I'm marketing our business, we kind of downplay weapons part and talk more about the other applications. Okay. What we didn't hear much of back in the Mound days that I remember was the presence of tritium in the nuclear power plants. Actually, as a byproduct of the nuclear plants that we have. What they found was in Europe, when they were decommissioning sites, they started seeing a lot of tritium. And so today, especially decommissioning sites, but even active sites. I don't know if you've read the papers. Chicago had a nuclear reactor a year ago that leaked some tritium into the ground. And so that's good for our business. People want to find tritium, and so they come to us to measure. So today's nuclear reactors have tritium as a byproduct, and we're seeing a renaissance of that. The next slide actually talks about something that's really fun, and that's the idea of fusion, which is getting closer and closer to a reality. We've got over 60 experiments around the world devoted to tritium fusion, and I think the next slide talks about, just lists all those places that are actively working, pursuing fusion research. And I don't know if you've... And later on, this was privatized, and now you'll find it at Los Alamos and other places are finally coming around. Next slide. The advantage of that ion chamber, and there's a unit sitting on the table over there, that when Mound was closing down, we basically wanted to box up and throw away all this stuff. which struck me wrong because I knew what it took to put it together in the first place. So we worked with the folks at Mound with an idea that if you have everything surveyed, say it's clean, spend the money to survey it, we can save the money in repair because now we can just replace and then we can work on it when we have the time. And so we wound up with several of these units that eventually wound up at Los Alamos for service. And what made the Mound unit unique was this finned electrode. Remember the first ion chambers, the Cannaes, the big ones, and then the Overhoff, they all had a straight rod in the center. Well, the guys in the T building, Reinhammer and Kershner and Burgess and many others, experimented with the design of that center counting electrode. And they wound up saying a four-finned approach simulated what was best, which was a cylinder within a cylinder. It gave you very linear response. And this was an empirical, very Edisonian sort of thing. They just kept trying and trying and trying. And they came up with this, and it proved to be a very good design. It allowed us to measure linear over a wide range and use a low voltage, only 24 volts. So now we could actually evacuate the chamber and nothing would happen. So lots of advantages here. The next slide is another thing you've probably seen down in the T building. We call them scoreboards or hang downs, and it was just like a scoreboard in a high school gym, and it would tell you what the tritium in the room and the tritium, I believe, in the duct or the duct was doing, and also had a real loud alarm inside it. And it wasn't much fun to calibrate because you'd always end up sending that alarm off, and it was right in your ear. But these guys had a sample probe and the little red button on the bottom to silence it when the alarm did go off. So it was a real nice thing. It was a real tough thing to engineer, as I understand. And folks at Gym City, I think, built them for Mound. It was tough to make this scoreboard configuration. Next slide. This is where, after they built that finned electrode, Carl Kershner sat down at what he called a computer at the time. It was kind of the beginning of computers, and figured out why the finned electrodes produced a linear result, why they worked. And now this equation is basically why an ion chamber produces the current that it produces. But the point of showing all this is to explain that ion chambers only see ionization. And if you look through the variables in this equation, you see that it doesn't say tritium ionization, it just says ionization. So if I had smoke from a cigarette, if I had a welder working, the biggest problem we saw at Mound was the DP&L plant had this big old pile of coal making radon. And the radon would creep up here and we could see the radon on our instruments. So that was an issue. Another variable is what kind of gas are you measuring the tritium in? With an ion chamber, it matters what the gas density is. And we'd have tritium monitors calibrated for measuring in room air. And then we put them in an argon glove box. And we'd wonder why we didn't get the right answer inside the argon glove box. And it's because the argon was affecting the output current because it was changing the density of the gas. So several things go into perturbing the ion chamber. I think the next slide talks about these perturbing factors that the electronics guys were always chasing down. When somebody had a tritium monitor that didn't read 0, it was an electronics job to see why. And the neat thing is our monitor was finally fast enough to see these excursions, whereas the big Cannae, it couldn't see it. It was so slow, you could have a little spike and it was all over there. So there's just two schools of thought. One is I want to see the meter read 0. The other guys that make the instruments like to see it move around a little bit, so it's still working. Next slide. Tritium Bubbler. And I hate to talk about this in front of Warren Sheehan because he knows way more about it than I do. But the Tritium Bubbler was actually a very great innovation for measuring tritium. It took that oxidation idea and combined the idea that ethylene glycol likes water. And the folks at Savannah River to this day still think that mole sieve and things like that, solid collectors, are the best way to collect water. And the folks out at Los Alamos still think that water is the best way to collect water. Well, at less than 10% relative humidity, water isn't too bad at collecting water. But at our humidity levels, it's not a very good way of collecting water. So by combining the really efficient oxidation process and selecting a palladium sponge as a catalyst, not using a ceramic coated catalyst, but a solid pure palladium in a sponge form, so you had all this surface area. You didn't get much holdup at all in the oxidizer. And with the ethylene glycol and the 3 vials, you guaranteed collection of the tritium. And to this day, the regulators really prefer that Tritium Bubbler as a means of measuring environmental tritium. And the nuclear power plants are starting to catch on that this is a good thing for us to have as a tool. Next slide. This was the one of the early, like I say, Warren's probably got a really good memory of what these are, but this is the earliest bubbler that I can find and a picture of. And it's an ongoing experiment with how do we bring in a reliable sample. The thing about the bubbler, it doesn't measure anything. It collects tritium, and you measure it in a liquid scintillation calculator. So what you do have to have is a value for how much air flowed through the bubbler so that you can do the calculation. So the means of accumulating the gas flow became very important. The reliability of the thing, these things ran 24 hours a day, 7 days a week. They were only to be attended to once a week when the RCT came and changed the vials of ethylene glycol. Other than that, they were on their own, and we didn't want to have to deal with them. So the components picked by Ben and Warren and Carl and all the people involved have proven over the years to be very reliable components. And to this day, we still don't deviate from the main components put in this engineer. I think the next slide shows what was finally made into the instrument you see on the table and what we ended up putting around Mound. Not the perimeter bubblers. The perimeter bubblers are not that nice, but all the stacks and even some rooms had this type of bubbler, which does do the accumulation of the flow rate. It does the measurement and control of the temperature, and we have the gates on the front. You might wonder, why do I have to have the gates? Well, when you've got a very small flow of a few cc per minute flowing through the ethylene glycol, it doesn't take much differential pressure for that glycol to just move from vial to vial, and you've got a real mess. You kind of lost a lot of your data that way. So we put the gates on there so that in order to get the vials off, which meant as soon as you unscrew the vial, now everything's atmospheric pressure at that point and whatever sampling pressures you were at the front and back. When you lift the gates, you put the inlet at atmosphere automatically. So the whole system went to an even steady state. We didn't get that glycol moving all around the system. Next slide is we've continued to work on this. This is kind of a schematic layout of what goes on inside the bubble. Same thing. Oxidizer, vials, and a flow rate. Next slide. The Tritium Bubbler, as I said, is probably, I think it's hard to argue that it's got to be the most sensitive means of measuring tritium. But you have to remember that's coupled with the liquid scintillation detector. But it does a great job at segregating the species. We separate the elemental tritium from the water tritium, the HTO, and the organics, which are much more dangerous to us. And so you have a separation of measurement, and you have a preservation of measurement, so that after the excursion has happened, you have 10 more tries at measuring that same sample before you run out of samples. So it gives you a lot of recourse if you want to retry your samples. Next slide. Ethylene Glycol. I don't understand this so well because I'm not a chemist, but ethylene glycol does a tremendous job at capturing water, and that's sort of the equation for why that happens. But the important thing is that we do have this ability to differentiate the species and resample multiple times. And the cocktail used in the liquid scintillation counter, the Ultimate Gold, was created no additional disposal problems, so the sample itself was all we had to worry about. We didn't have this mixed waste issue. Next slide. And we did many experiments. I know I've seen Carl's done a lot of these and others, where the run time of the unit was compared with how much tritium was collected in each vial. And I have customers today that still ask, well, why do you have 3 vials? Why do you sample for a week? Why not longer? Why not shorter? Why not less vials? Why not more? It's great. All I have to do is show them this data. It still holds true today. Next slide. Some of the other means of measuring tritium were Bob Ellison's TAM, and I think most people are familiar with. A beta scintillation detector is what it was. This is a device that measures high levels of tritium, gives you the partial pressure because it has a europium doped crystal that scintillates when it sees the beta energy. And so we're looking at a photomultiplier tube looking at this scintillating crystal, and that's another means of measuring tritium. Next slide talks about bioassay. Now this is something that's strange to people that aren't familiar with tritium. Most people are familiar with dosimeters. If they've seen anything with radiation, they know people wore dosimeters, and that's how you measure the radiation people have. Well, tritium doesn't show up on a dosimeter. So we had bioassay programs, and we had to leave our samples when you entered the facility, when you exited the facility, depending on the job and the time frame. The frequency got to be pretty frequent. Also noted is the same technique of liquid scintillation counting for bioassay and environmental is used, but we always kept those separate so we wouldn't cross-contaminate the facilities. Next slide talks about the Mound systems that are maybe you can talk to some people that want to discuss this further. I don't know if Don Hobrock touched on all the monitoring and all the great things that happened down in T building when he talked. But in T building we had a really neat facility for its time. We had a central control room where you could see all the rooms from this one vantage point and know if there was a problem. And we had a computer that Ken Foster pretty much kept going, and that stored all the tritium data at that time. In other areas, we had isotope separation systems to purify tritium. We had test labs. We could actually recover the tritium from our aqueous waste, and just a tremendous number of tritium technologies. Next slide talks about other topics I'd like to hear more about. And one is this document called the Tritium Control Technology document, where a survey of the country's tritium facilities was done, and we kind of had a a snapshot of best practices throughout the complex, and that went to be used here. Another is the American Atomic Store, where this watch company in Tucson, they would test their luminescent tubes by putting them in a bag of water, essentially. And if they had a leak, of course, the whole bag of water was bad. What do you do with that treated water? Well, they put it up on the roof, which was not a good idea because the authorities found out about it. And from what I understand, Lambert or Neuenhammer spent the better part of their summer out there seeing over some of the cleanup. I don't know if other people have got to go out or not, but I think we have to buy from overseas pretty much today. International Tritium Symposium. The first two were held here in Dayton for it's a global event. They're still doing those today. The last one they had was in Rochester a year and a half ago. The next one, I think, unfortunately, is in Japan. So, kind of expensive plane ticket. A basic tritium training class, that was super. I don't know how many of you took it, but it's a week of nothing but tritium training. And we started with the Mound folks, and then we had people from all over the complex coming in and learning how to work with tritium from the experts here at Mound. And we just had so many great contributions from Mound, and I think everybody ought to be proud that out of necessity, because we were in the neighborhood, because we had to act this way, we had a really good program and really advanced tritium technology quite a bit. Next slide talks about, this is where I turned into commercial mode to talk about our group. We still sell, Mound Technical Solutions still sells Tritium Bubbler, the TAM under the BSD name. We're working on other tritium instruments. We also do fuel cells. If you ever get a chance, we're over at COS Drilling, first, second, and third floors. That's some of our crew: Bob Ellison, Steve Huff, Tom Kershner. Chris is a new guy, didn't work at Mound, a great programmer, and obscure chunky guy there behind Tom. So if you ever get a chance, just come over, give us a call, and we'd be glad to talk to you. Next slide. Here's the TAM that Bob actually, Bob left Mound and worked 10 years at Inficon working on mass specs where he developed some really neat things. When he came back to this area, we joined up and we had some customers that wanted the BSD, and so we revamped the design with some new materials that were available, and so we offer that product today. Next slide is a product we're doing with Los Alamos National Lab, where this device will measure process levels of tritium in real time, so that Ray doesn't mind if I say we can get rid of the calorimetry of the tritium and measure our inventory in real time instead of shutting down for a week or two every quarter to measure the tritium. And that's a picture of the researcher Steve Pagliari that developed co-developed the technology out of Los Alamos. Next slide, I think, is our fuel cell products, and just a myriad of things for fuel cell technology, which does have some ties to what we learned in the tritium. And the next slide shows a new mass spec system that we put together based on Bob's know-how and understanding of mass spectrometry. And while this is intended for the fuel cell industry, it's used, it can be used in just about any other application that needs a mass spec. But the interesting thing is, mass specs are tough to use. I talk to a lot of people that have a mass spec in their lab, and they don't do anything with it. One, because it may not work. Another, because they don't know how to get a sample from it. And a third, if they do get the sample, they don't know what to do with the data. So we're really graced with Bob's help in helping us put together a package, which is a sample system that automates the sample pulling and stamps it with some other data so that we can correlate what's going on, and then sort through all that data to tell you what is in the gas. Just here's a report of what was in the gas. You don't have to figure it out on your own. And it's pretty neat. So we're really looking forward to getting all that launched. I think the next couple slides are just some interesting projects we've done. This was a leak tester, and we successfully were able to leak test a real thin MEA. Another thing we've done is found a way to measure gas flows at virtually no back pressure and at independent of gas species, which I don't know how familiar you are, but most automated means of measuring gas flow is very dependent upon the gas density and what's in the gas. And also most automated techniques require some sort of differential pressure. You got to have differential pressure to have flow, but most of them require pretty significant differential pressure. And in some of today's new applications like biofuels and so on, you just can't present that back pressure. You don't know what your gas is, and so you've got to be device for measuring that. And the last slide is just a reminder to give us a call or visit our website, and let's keep the dialogue going about tritium technology and things we did at Mound. I think we've got a great resource here. The museum has a wealth of information with the MLMs and documents that people are reinventing this stuff every day. And it's interesting the phone calls I get from people wanting to know things. And I get a hoot because if I can't answer them because I've got the document laying right there in front of me, I got all you people I can just call up and say, what's the answer to this? And I get to solve the problem. So that concludes my presentation, and thank you for having me.